We can think of the trapezoidal rule as using first-degree polynomials to approximate the area under the curve, right? So we pick any 2 points whose endpoints are from the division, like we've got x0 and we've got x1. So this is our first subinterval. And we find the points on the curve. And we say, well, we know that the function doesn't follow this straight line, but lines are easy to deal with, so we'll just connect with that straight line. And so we'll use that, that linear approximation, right? So it's kind of a secant line approximation of the curve. So recall the formula here. We have 1/2 times the height here is f of x0. And the height here is f of x1. And then we multiply by that width, which is delta x. And I should have mentioned this curve is, you might have guessed, we're calling f of x. So this would be the area of that first trapezoid. And this is just a quick review. So x1 to x2 is going to give us a second trapezoid. So that's going to be plus 1/2 times f of x1 plus f of x2. And then again, that's going to be the average of the bases, and then we're going to multiply that by the distance between the two bases. That's our delta x value. So that works out pretty well, but what if we decided instead of using degree 1 polynomials, we use degree 2 polynomials? In other words, parabolas. Okay, this is going to open up the door to something called Simpson's rule. So what we're going to do is, this is the same function, f of x. This is the same function, f of x. And these are the same intervals, x0 to x1 and x1 to x2. And we're going to pick these same points on the curve, but instead of using lines to connect them, we're going to use a single parabola that goes through all 3 points. Okay, so you might have done this in the past where, well, you've definitely done this in the past where you were given 2 points and you found the equation of the line. But hopefully in Algebra 2 or maybe in pre-calculus, you also were able to find the equation of the parabola given 3 points, and you could do the same thing with the cubic using 4 points or a quartic using 5 points. We're not going to get into that, but you could. So anyway, we're not going to actually derive the formula here, the area formula for this region that's bounded by these 2 vertical lines, the x-axis and that parabola. But we could go through this process at some point in the future once we learn the fundamental theorem of calculus. But it works out that the formula for this orange shaded region here is b minus a. Well, we don't have b's and a's here. I guess I'll use x2 minus x0 divided by 3 times f of x0 plus 4 times f of x1 plus f of x2. Okay, so this is a single expression to find the area of this region bounded by the parabola and those 3 lines. And again, the parabola isn't our original function. Our original function is curvier than that, right? It curves back down over here. So the parabola doesn't quite follow the curve, but it does a better job than the lines. I mentioned this a minute ago, but make sure you understand that we actually need 3 points to determine that parabola. So that means that we need x0, x1, and x2 in order to use this formula, which means that we actually need 2 subintervals to get 1 piece of area. What ends up being the result of this is that n has to be an even number because we have to be able to pair them up. So let's compare the process between these 2 different procedures. For trapezoids, we have a common delta x, that's b minus a over n, and we have a common 1/2. If we take a look up here, when we were adding up our areas of our 2 trapezoids, notice that the 1/2 showed up in each of the trapezoids, and that delta x showed up in each of our trapezoids. That is going to be the same for each trapezoid, assuming we're using equally lengthed subdivisions, which we normally do, subintervals. So we can factor those out, and we end up looking at f of x0 plus f of x1 plus f of x1 plus f of x2. And you can imagine that, in fact, you've probably seen this if you've already worked some of the trapezoid problems. You can imagine that we can continue this if we need to with more trapezoids, if our n value is bigger than 2. And we can go f of x2 plus f of x3. And maybe I'll do just one more and do f of x3 plus f of x4. Okay, and because this is all addition, we know that we can associate these in whichever way we want to. So you'll notice that we can combine these two together to get 2 times f of x1. But we don't have two f of x0s. We just have a single f of x0. But we have two f of x2s. And we have two of all of the ones in the middle. And I believe we mentioned this earlier in the last video. But the first one and the last one only get used once, but all the ones in the middle, all these ones in the middle, get used twice. Okay, and that's a pattern that we see with the trapezoidal rule. With Simpson's rule, we have a similar thing that can get factored out, and that's this guy right here, this beginning minus end divided by 3 this time. Okay, so x2 minus x0 over 3 is going to be the same thing as x4 minus x2 divided by 3, etc. So that's why it's always going to be the same. It's not b minus a over n anymore with the 1/2, but it's b minus a over 3n. And again, I didn't get into why that is. That's a proof for a later date. But if we were to continue this to a second and maybe even third parabola, again, the b minus a over 3n got factored out, but our next parabolic chunk is going to start off at x2, f of x2, exactly where the last one left off, right? F of x1 is where we left off here. We picked up where we left off because we've got that common border between the two trapezoids. Same idea here. We're going to have that common border between the two parabolic chunks. So we're going to pick up where we left off, but then we have the next one, which is going to be the middle one has that coefficient of 4, and then we have f of x, let's see, we're on 3 now, right? F of x3, and then we end up with a single f of x4. And just for fun, maybe I'll say we have 3 different parabolic chunks. So I'll do one more of these. We'll add up, again, picking up where we left off at f of x4, and then we have 4, that coefficient of 4 is always there. F of x5 would be the next x value, and then we've got a single f of x6. So the idea here is very similar to that of the parabolas, but you'll notice we've got a single f of x0, and we have 4 f of x1s. Oops. And we have 1, 2. F of x2s, right? We have 2 f of x2s. And we have 4 f of x3s. And we have 2 f of x4s. And we've got 4 f of x5s. And I think you're seeing the pattern here. I hope you're seeing the pattern. And then finally, we're going to end up with, we're not going to reuse the very last one because it's the right end of the rightmost segment of area. So it's a similar sort of pattern. We have a coefficient of 1 at the beginning for both of these. We have a coefficient of 1 at the end for both of these. And in the middle, for trapezoids, we had 2 over and over and over again. In the middle, for the parabolas, we have an alternating 4, 2, 4, 2, 4. And it always starts and ends with 4. We can't end with a 2 here. And hopefully you're starting to understand why I said earlier that we have to have an even number for n. In this case, n equals 6. We use 6 subintervals. And we don't have to stop at 6. If we needed 8 subintervals, then we could go all the way to 8, and we would just have a couple extra terms in this mix. So we can kind of summarize these two different methods. The trapezoidal rule, that we already talked about, in the last video, and now this new Simpson's rule, which is, you could call it the parabolic rule if you want to. Notice a lot of similarities here. We have the b minus a over n both times is a 2 versus a 3, but they're similar. And then the coefficients of 1 at the beginning, at the end, and then the ones in the middle get reused. But again, that other big difference is the alternating 4, 2, 4, 2, 4, 2, 4 instead of just the 2, 2, 2, 2, 2, 2, 2. So yeah, that is Simpson's rule.